it's Miss Miklos here, and this lesson is over solving. And in order to solve, we're going to have to think back to last chapter when we learned about our sine graphs, our cosine graphs, and our tangent graphs. So we're definitely going to use these three graphs to help us out in determining what our solutions are going to be. So what you guys will see is that today we have two major sets of problems. The first is telling us to solve over the set of all real numbers and use radians and round to the nearest hundredth. So when we see this and it's telling us to round, that means that we need to be using our calculators. So the very first thing that you should do is go ahead and make sure that the mode of your calculator is in radians. Number 1, we have 5 plus 7 cosine x equals 0. So the very first thing that I'm going to do is isolate cosine. So I'm going to subtract 5, and I get cosine is equal to negative 5 over 7. And before we do anything with this, I actually want to sketch a quick graph. Okay, and so here's our graph. I know this is 2 pi, and this is pi. And this is all based on what we did last chapter. We know our cosine graph starts at 1, 0, negative 1, 0, 1. So I only just graphed one period. We know that it continues in both directions. Now negative 5/7 is somewhere down here. Okay, and I know this isn't exact, but that's okay. And one thing I notice is that it looks like these intersect two different times over this period. So we actually have two different solutions. The way that we are going to find our first solution is by using our calculator. And remember, the way we put this in our calculator would be cosine inverse of 5/7. And when I put this into my calculator, I get an answer of 2.37, and then I know that it is happening every single 2 pi because this graph continues and it's going to cross again and again and again. And so every single 2 pi, because that is the period, we're going to have another answer like this. So what we're going to do, we're going to add 2k pi. K represents a constant. So this would be like adding 2 pi, 4 pi, 6 pi, a million pi, etc. So this is my first answer, and in fact, this is my answer that was right here. Now, we notice that we have another answer that our calculator did not give us. And so the thing that I notice about this graph is that it is very symmetric. In fact, if I folded right down the middle here, it would look exactly the same. So what that's telling me is that the distance from 0 to our first answer is the same as the distance from 2 pi to our second answer. So whenever I have cosine, and I should put cosine x there, the way that we always find our second answer is by doing 2 pi minus the first answer. So the first answer is given to me using my calculator. The second pi, I'm doing 2 pi, and I'm subtracting this much, and we already said this is the same distance as here, which gives me the second value. And so when I put that into my calculator, I end up getting an answer of 3.92, and I know this is plus 2k pi as well because it's happening and repeating every single 2 pi. So these are going to be my two different answers. Now, we definitely could have done this without using our graphing calculator, without graphing it. However, it gives me a really visual picture as to why we get these two answers and where they actually come from. Number 2, we have a sine problem here. So the very first thing I'm going to do is isolate sine. So I'm subtracting 5, and then I'm going to go ahead and divide by negative 13. So I get sine of x equals 5/13. Off to the side here, I'm just going to go ahead and graph a sine graph just so we kind of remember what that looks like. I know sine starts at 0, and then 1, 0, -1, 0. So this is what that looks like right there. And sine of 5/13 would be somewhere over here. And once again, I notice that it looks like there are 2 points of intersection. And we know that this is going to repeat, so these 2 points are going to repeat every 2k pi. So let's go ahead and put this into my calculator to find our first answer. So I'm going to do sine inverse of 5/13, which ends up being 0.39 plus 2k pi. Now, this time, in order to find our second answer, something looks a little bit different about my graph. In fact, this time, it looks like this distance from 0 to my first answer is the same distance as pi is from my second answer. So whenever I have sine, the way that we're finding our second answer is pi minus our first answer. So I'm going to go ahead and put that in my graphing calculator. And I end up getting 2.75 plus 2k pi. Okay, and once again, this 2k pi is telling me that these 2 points are repeating if I add 2 pi to them, because I know my graph repeats every single 2 pi because that is our period. So kind of to sum up what we've seen so far. Cosine, we have 2 answers. The second answer, we do 2 pi minus the first answer. For sine, we have 2 answers. To get the second answer, I do pi minus the first answer. Number 3, we're moving on to tangent. So same thing, I'm going to go ahead and isolate tan. So I get tan of x equals 7/8. So if I'm sketching a graph of our tangent, okay, I know our period is at pi. Those are my asymptotes. And I know that it's going to go up 1 over 1, down 1 over 1. So this is kind of what my graph looks like. Now in this case, I have 7/8, which is like right here. And this one looks kind of interesting because it appears as if we only have 1 point of intersection. So what we're seeing is that sine and cosine, for most of our problems, we have 2 points of intersection. For tangent, we only have 1. So in a lot of ways, tangent is the easiest one to deal with. So in my calculator, I'm going to do tan inverse of 7/8, and I get 0.72. Now, I need to think of what to add because I know this repeats. However, we learned last chapter, tangent does not repeat every 2 pi. It repeats every pi. So my answer here is going to be 0.72 plus k pi. Okay, so number 4. Once again, I'm beginning by isolating my trig function. So I get cosine is 1/4. Now, at this point, we've kind of seen what they visually look like. I'm going to draw them out each time just so we can kind of see. But keep in mind, we could definitely do this without drawing it out if we know what our pattern looks like. Okay, so I know to get my first answer, I'm going to do cosine inverse of 1/4, which is 1.32 plus 2k pi. Okay, so I really figured out that this distance right here is 1.32. Now I know this distance from 2 pi to our second answer is also 1.32. So I'm going to go ahead and do 2 pi minus 1.32, and I get 4.97 plus 2k pi as our second answer. So just to review, I did 2 pi minus 1.32 to get that value. Okay, number 5. Number 5 to me is kind of strange because it's already isolated and it's set equal to an integer. And in fact, I'm going to go ahead and sketch this out here. Okay, I know that this is what our graph looks like. And it looks like I only have this answer once in our entire period. Okay, it only touches 1 once. So since we're using our calculator, I'm going to see what is sine inverse of 1. And I get 1.57 plus 2k pi. Now, I know that's my only answer by looking at this graph. Let's pretend, though, that I didn't graph it out, and I went ahead and did pi minus my first answer, because I know that in sine, to get our second answer, we do pi minus the first answer. So in my calculator right now, I'm doing pi minus our answer, and I actually get 1.57 plus 2k pi. So notice that even if I didn't graph this one out, I get the same answer again, so that lets me know that this is our only solution for this particular trig function. Number 6, once again, I'm going to isolate sine. Hopefully we're kind of seeing that this is a very repetitive process where we're really doing the same thing every single time. So I get sine of x equals negative 4/7. If I'm sketching a graph of this, okay, I know negative 4/7 is down here somewhere. And we do see that we see 2 different points of intersection. Okay, so in my calculator, I'm going to do sine inverse negative 4/7. And something kind of weird happens here, because when I put this in my calculator, I get negative 0.61 as my first answer. Okay, and looking at where I've graphed this, neither of these 2 points is negative 0.61. However, if I continued going this way, this point right here is actually negative 0.61. So in order to find my second answer, since it's sine, I'm going to do pi minus negative 0.61, because I'm doing pi minus my first answer. And I end up getting 3.75 as my other answer. Okay, so what I want you guys to know is this negative 0.61 is equivalent to this answer. 3.75 is equivalent to this answer. So we do have both of our solutions, and these are correct answers. Notice my 2k pi is reminding me that it's repeating every single 2 pi. Number 7, we have a cosine one. So once again, I'm going to start by subtracting 5 and then dividing by 3. And let's say you guys didn't graph this one and right away put this into your calculator. Something really strange happens, and it tells you that you have an error. And often when we see error, we think we messed up, but let's go ahead and kind of look at what this graph looks like. Okay, I know cosine starts at 1, and negative 5/3 would be somewhere down here. And what I notice is that these two graphs never intersect. In fact, we've talked about this a little bit before, but sine and cosine can never be greater than 1 or less than negative 1. The reason being, our hypotenuse is the denominator, which means that that's the biggest side. So the denominator will always be bigger, which puts it between 1 and negative 1. So our answer here is actually going to be no solution, because there are no solutions for this particular equation, because there does not exist an angle where cosine can be negative 5/3. Okay, our last problem using this method, I'm going to go ahead and start by subtracting 4 and dividing by 9. And just kind of a side note, in our previous problem we said sine and cosine can never be greater than 1 or less than negative 1. However, in tangent, anything can happen. And the reason being is that tangent is opposite over adjacent. So it can be greater than 1, less than negative 1, because it continues forever up and forever down. Okay, once again, negative 4/9 would be somewhere down here. And I notice that there's only one point of intersection. So in my calculator, I'm going to do tan inverse of negative 4/9. And I end up getting negative 0.42. And since this is tangent, I'm just going to add k pi onto that because it's repeating every single pi. Okay, so the second concept that we're learning is to solve exactly. Whenever we see exactly, we know that we should not be using our calculator at all. And so we're going to have to rely on some of these trig functions that we have previously learned. Now, today we are going to be working in terms of radians, so it is important that I know radians really well. Can we convert it into degrees? Yes, we can, but I'm just going to work in radians today. So we know when we're dealing with 0, sine of 0 is 0, cosine of 0 is 1, tan of 0 is 0. Pi over 6 is equivalent to 30 degrees, so sine is 1/2, cosine is radical 3 over 2, and tangent is radical 3 over 3. For pi over 4, our sine value is radical 2 over 2, cosine is radical 2 over 2, and tangent is 1. For pi over 3, we have radical 3 over 2 as the sine, 1/2 as the cosine, and radical 3 as our tangent. Lastly, for pi, our sine value of pi is 0, cosine is -1, and tangent is 0. So this just gives us a glimpse at these values that we need to know. And we're really used to working in a sense of saying, okay, well, what's sine of pi over 4? And we have to give radical 2 over 2 as the answer. We're going to have to be working backwards, where it'll be like, what angle has a sine value of radical 2 over 2? So we need to know these values very, very well. We should have these memorized from last chapter, but if you don't, you must spend some time making sure these are memorized. So looking at number 1, the way that we're going to start this is very, very similar. So I'm going to go ahead and subtract 1, and then I'm going to isolate sine by saying sine of x is equal to 1/2. So I'm just going to sketch out a graph once again just so we can kind of remind ourselves what this looks like. But I know this looks like that. Sine of 1/2 would be up here, so we can definitely see that there are two solutions. And I need to think, what angle has a sine value of 1/2? And if I have those values memorized, I should know that it is pi over 6 that has a sine value of 1/2. So my first answer here is going to be pi over 6 plus 2k pi. Now, since this is sine, I know to find our second answer, we're going to have to go ahead and do pi minus the first answer. So when I do pi minus pi over 6, I end up getting 5 pi over 6 plus 2k pi. So these would be our two answers. Notice the only thing we did differently was instead of putting this into our calculator, we had to rely on our memorization that pi over 6 is the angle that has a sine value of 1/2. Looking at number 2, we already have sine isolated, so I need to think what angle has a sine value of radical 2 over 2. And I know that that is pi over 4. So I'm going to say pi over 4 plus 2k pi. And let's go ahead and just sketch this out again just so we can kind of remind ourselves what this graph looks like. We should be experts on this graph. Radical 2 over 2 is like 0.7 approximately, so that would be somewhere in here. So I can definitely see we have 2 points of intersection. So I'm going to have to do pi minus pi over 4, which ends up being 3 pi over 4 plus 2k pi. So those would be my two different answers for number 2. Hooray, number 3, we have a tangent problem, which I know is the easiest because we know tangent only happens once. So I'm subtracting radical 3, and then I'm going to go ahead and divide by -3. So I need to think what angle has a tan value of radical 3 over 3, and that is pi over 6, and this is only repeating every k pi because the period for tangent is just pi. Number 4, I just want us to kind of focus on number 4, and the reason being is that since it's equal to 0, I'm thinking that this might deal with some of our quadrantals. And my guess is you guys probably haven't thought of this in this way before, but whenever we label our typical cosine graph, each of those 4 marks are actually our quadrantals. And when I sketch a graph of cosine, there we go, I can see exactly where it crosses. In fact, I can see that my first answer is pi over 2 plus 2k pi. Now, my second answer, since this is cosine, I could do 2 pi minus pi over 2, and I would get 3 pi over 2 plus 2k pi. Or I could look on the graph and I see that. Now, there's something very significant about these two answers, and in fact, if you put this, technically you're not correct, because there is a better way that we can write this. And what I'm noticing about our two answers here is that these are actually just pi away from one another. So what that means is that I can actually condense my answer to say pi over 2 plus every pi. Okay, because that's saying it works here, and then it's going to work here in a pi, and then in pi it's going to work. If I go backwards in pi, it's going to work. Okay, so often when we have these ones that deal with quadrantals, we have to think a little bit more about it. So this is the best way to write this answer because it is as simplified as possible. Okay, so number 5 looks similar to number 4 did in the fact that we're dealing with 0, so I'm probably thinking a quadrantal problem. And if we look at our graph here, I can see sine is at 0, at pi, at 2 pi, at 3 pi, at negative pi, and it continues in all directions. So my answer is just going to be k pi, because this is telling me it's happening every single pi. Number 6 looks difficult because I have 2 different trig functions. However, I'm going to use all of our knowledge that we've learned in this chapter, and I'm going to divide both sides by cosine. And I know sine over cosine is tan. Cosine divided by cosine is 1. So working on this, I need to think what angle has a tangent value of 1, and that would be at pi over 4. Since it's tangent, I know our answer only happens once, so my answer is going to be pi over 4 plus k pi.